I'm Brett Jackson, and I'll be reporting on our paper titled Archetype and Tilt Type Pen-Based Immersive Text Input for Room Scale VR. And this work was done in collaboration with Logan Carrico and Zahara Spilka, who are both undergraduates, seniors at Macalester College. The particular topic that we're looking at is how to do text input in virtual and augmented reality, which currently remains a challenge, particularly for room scale applications where you can't necessarily be tied directly to a mouse or keyboard. And one of the areas that we were particularly looking at is whether pen-based VR controllers may present an alternative because they use the fine motor control of the fingers to actually improve performance. There's two main areas for text input in VR. The first is speech. So Swifter was one particular interface that looked at this. And one of the issues with speech is that it doesn't work very well in noisy environments. And it also is problematic when you're trying to input something private, like a password, if there might be others in the room that could hear. So many people have started to look at whether or not we could actually use physical keyboards in VR or AR to type, because people are very quick at typing in traditional keyboards. And so there's been a lot of recent work looking at how to add visual feedback that can improve typing performance. So for example, the work here at the bottom is showing different ways of representing the avatar's hands to improve performance. Now, the downside to this is that usually the user has to wear some sort of tracking, and if you want to combine using some sort of camera system so they can actually see their hands, then they may have to be in front of a green screen. And this doesn't work in room scale applications like a VR cave or even a HMD where you want to walk around and use physical navigation because you're tied to the keyboard. So others have looked, for example, the hockey interface mounted a keyboard on a wearable system to walk around with it. It, of course, has some downsides in that ergonomically it's just a little bit hard to type with. So in our own work, we wanted to see whether or not we could use gestures or controllers to interact and provide text input. And I should mention that all of these systems with gestures and controls are going to be slower than using a physical keyboard. But they may still be useful for particular applications where a small amount of text needs to be entered, like searching or adding login information in some sort of prompt. The most common and the standard one is to do what's called controller pointing, where you cast a ray from the controllers and intersect with a virtual keyboard, and usually that confirms the selection with a button press. And that's the system we actually used to compare with the two interfaces that we're presenting today. Others have looked at gestures like pinch gestures to select different keys, or even using the touch sensor on traditional VR controllers as well. But one of the issues with these controller-based interfaces is that you're using a physical wand, and there's been some recent work that has found that actually using pen-based devices may be faster. So the study by Pham et al. Here at the bottom compared a traditional wand to a mouse and a pen and found that actually the pen had comparable throughput in a Fitts law task to the mouse, and actually outperformed the standard controller because it's used with a precision grip that allows fine motor control compared to the power grip of actually holding a wand in your hand. We're starting to see more pen-based devices coming to market, like the Logitech VR Ink or the massless IO pen. But there's still relatively little work looking at how we could actually use these for text input. One notable example is the virtual notepad, which allowed you to write, but it didn't actually convert your drawn letters into actual characters that are recognized, and that still remains a challenge for handwriting. So in our own work, we were interested in how we might take the fine motor control of a pen, but use it in a way that's not just doing standard handwriting. And so we present two interfaces, tilt type and archetype, that do this for room scale, and this was actually implemented in a VR cave system. The stylus we're using is the OVR stylus, which is a custom-built pen, if you're interested in the publication details for that, see our paper. The first interface, tilt type, uses a horizontal binned layout, so the letters are oriented in vertical bins. And there's an alternative layout for numbers and special symbols. And those can be chosen by just clicking a secondary button on the stylus, and it swaps between which layout is currently chosen. In order to pick a particular bin and a particular character within that bin, we use two different gestures. So small rotations left or right will change the bin, and tilting the stylus away from the user will select a character within. And then if you click the button, that confirms. And that's easily seen with a video. So here the user is just making small hand gestures to select bins and individual characters. So tilting left or right, we'll select the bin. And tilting away from the user, we'll select a character within the bin. And those are confirmed again with a button press. Our second interface is archetype, and while tilt type looked at these small fine motor control motions with the pen, archetype was examining whether or not we could combine larger wrist rotations with small finger motions on a slider on the pen. So the OVR stylus includes a touch slider, and we use that here. So rather than having a linear layout, as you can see on the right side of your screen, the bins are oriented in a radial layout, and small angular rotations will pick a bin. And I should make sure to make this clear, this is not using ray casting, it's actually using the angular rotation of the stylus to select the bin. And then sliding the finger along the touch slider will select within the bin, and removing the finger confirms the selection. So again, we'll see a video. And we do give some visual feedback here with a virtual stylus shown in front of the bin. So angular changes, change the bin. And then sliding along the touch slider will change the letter within the bin, and you remove your finger to confirm. In terms of evaluation, we couldn't run a study because of COVID-19, an in-person study, and so instead in the paper we present an analytical discussion with one of the authors using the two interfaces. And to provide a point of comparison, we implemented the standard controller pointing or raycast interface where a ray is intersected with the standard QWERTY layout on the screen. For this comparison, we use 36 sentences chosen at random from the Mackenzie phrase set, which is a standard phrase set for evaluating text input. There's some statistics here about those sentences. For each of the interfaces, the participant was asked to do 2 practice trials where they were given a prompt that they try to replicate, and then 5 blind, where it doesn't show the output that they're picking, it just shows whether or not they've output a letter. And then 5 perfect, where it actually does show the output and they have to go back and correct errors to actually match the prompt before it will let them proceed. We looked at a variety of different metrics, and the first is entry speed, so words per minute. We use the standard definition of 5 characters equaling a word, and you can see the equation for that at the top. When we look at the results, raycast was the fastest at about 8.8 words per minute for blind and 6.6 for perfect, followed by tilt type, and then archetype was the slowest. And you'll notice these are fairly low compared to standard keyboards. That's actually expected, and the raycast is consistent with prior studies as well. One of the things to also note here is that the perfect trials are all slower than the blind trials, and that's to be expected. It takes longer to go back and correct errors. We were also interested in the percent error rate, and to do this, this only includes the blind trials because by definition the perfect trials did not have any error. And we calculate this using the Levenshtein distance, which is the number of character differences between the prompt string and whatever the user output. And we can see that tilt type was actually the most accurate. It had the lowest error, followed by the controller pointing raycast. And then archetype had the worst error at about almost a quarter of the sentences had error. So thinking about both speed and error and how these combine, one of the things we found is that controller pointing was the fastest, but it also had a fairly high error rate at the second highest error. And there are a couple of different things that we can use to explain that. So a prior study found that when users point at a target at some distance from them and they try to hold steady, they tend to have plus or minus 5 degrees, rotational degrees of noise. And it turns out that while that seems fairly small, if you take that difference down the length of the ray and see where it intersects the keyboard, the virtual keyboard at roughly 2 meters in front of the user, that can actually be a fairly large positional change. And this is borne out in the results as well, particularly related to the Heisenberg effect. So when you press the button to confirm on the pen, there tends to be a strong downward deviation as well. What we found is actually 100% of the raycast errors were selecting a character one below the target character that the user had wanted. And it's probably that Heisenberg effect that caused some of those errors. And that seemed to be actually exacerbated for pen-based controllers compared to standard VR wands for a variety of factors. One just being basic physics. The wand is a larger mass. They're usually bigger than the pens, and so it takes more force to move them compared to, button presses are still fairly small forces. The other issue is that wands are traditionally held in a power grip where you have a lot more control versus a precision grip. And in particular, we found that with the pen, you tend to hold it in roughly a 3-finger configuration. And when you press the button, if the button is not directly over the bottom 2 supporting fingers, those fingers actually act as a pivot point that help exacerbate the sort of rotation of the pen moving down. That didn't seem to be nearly as much of a problem for tilt type, as well as with the noise, because 5 degrees of rotation noise for tilt type was actually less than the amount of rotation needed to change from one bin to another, from one character to another within a bin. There are a few reasons why archetype probably was the slowest and had the highest error, and most of them relate to using the slider for input. Inherently, it's just slower to have to release versus just having a button press to confirm the selection. And also, when you release with the slider, you lose the haptic feedback of where your finger was in relation to the endpoints of the slider. And so when you put it back down, you have to take a moment to kind of figure out and use some proprioception for how far you've slid along the slider. The other issue is the implementation with the OVR stylus we were using uses a low-cost potentiometer, which works by changing the electrical resistance depending on where you press, and actually requires a fairly strong pressure to make it have a consistent reading. And that was found to be uncomfortable by the user and also led to likely higher error. One of the issues in terms of comparing the speed, there's been prior work that's also found that angular selection tends to have lower throughput than pointing, roughly 2.3 bits per second instead of 4.7. These were done using Fitts law tasks. And that's actually borne out in our study as well. So we looked at the amount of travel in terms of rotational travel that the user needed to accomplish for archetype and tilt type to select different letters. And you can define ideal travel using the equation there. And there's some more details in the paper. One of the things we found is that the movement tends to be broken into 2 different phases. There's a ballistic phase where you get a rough movement and then a correction phase. And it seems as if the users had to actually do a lot of correction, shown by there's actually a much higher amount of movement used than compared to the ideal amount of movement. We also looked at position, and one of the things we found is that the tilt type was the most comfortable to use, and that's likely because you could hold it at your side. It only depends on angular rotations, not position at all, so it didn't matter where you're held. And you can see that here in the orange is where the tilt type positions. The actual position didn't really change. It's much lower. It's held down at the user's side. It was a little bit more ergonomic, whereas the green is shown with controller pointing, where they actually had to physically move their arm quite a bit more. It can lead to more fatigue. So some lessons learned. If you want to advocate for speed and you don't want to use just a keyboard, controller pointing seems to be the fastest, but you need to account for these errors and jitter, which seem to actually be worse with pen-based controllers than traditional wands. If you want to avoid jitter and actually increase comfort and not have the sort of gorilla arm effect of holding your hand out in space, then you ought to favor angular-based approaches like tilt type. One of the things we found actually with tilt type is that it's much easier with the angles to pick outermost bins of layout, because the angular width for those bins, because you could actually rotate past where the selection would be, was easier. And so if you're thinking about different layouts, positioning commonly chosen letters at the edges is probably most useful. We would favor physical buttons over sliders because of the haptic feedback they have. And if you're going to implement pen-like controllers, you ought to use capacitive sensing rather than potentiometers for ergonomics. There are some limitations with a single user. It's hard to actually draw concrete conclusions. We couldn't run any actual statistics, but hopefully some of our discussion in the paper is useful. And all of these systems would be improved with some sort of autocorrect feature. There's also more work that could be done in looking at optimizing bin layouts, potentially based on letter frequency as well. So in conclusion, we present archetype and tilt type, which are 2 pen-based interfaces that provide a bit more information about how we should start to design pen-based text input interfaces.